Apache Cassandra is a distributed database that can handle large amounts of data with no single point of failure. Since 2008, Cassandra has been widely adopted, and the software and the community around Cassandra have grown steadily. A software developer interacting with Cassandra uses CQL, the Cassandra Query Language. ScyllaDB is another open source database that has been created to be totally compatible with CQL. By complying with CQL, the internals of ScyllaDB can be a vastly different software rewrite from Cassandra. ScyllaDB uses C++, whereas Cassandra uses Java. ScyllaDB improves upon the performance characteristics of Cassandra by optimizing for modern hardware. And Dor Laor joins the show today to discuss how ScyllaDB does all of this. For Q3, I am looking for sponsors. If you're interested in sponsoring Software Engineering Daily or you want to advertise on the show, please send me an email at softwareengineeringdaily@gmail.com. And if you enjoy the episode, please share it on Facebook or Twitter. The show grows by word of mouth, and the listeners have been very gracious in sharing, and I hope that continues. Also, if you have any questions about the show, any criticism or feedback, you can always send me an email, or you can just say hi. You can also just tweet at me. I'm very open to talking to people who listen to the show. After a message from today's sponsor, we will get to this episode, ScyllaDB and Cassandra with Dor Laor. I had a crazy idea a couple weeks ago. It's a photo sharing app that only has pictures of cats. When I finish my photo sharing cat application, I will be deploying it to Linode because Linode is the fastest hosted Linux provider. I don't want to get locked into a proprietary platform that's going to overcharge me as soon as my app gets popular. I just want a fast Linux server with simple pricing. Go to linode.com/SEDaily and get $20 in free credit today. Plans start at $10 a month, so my free $20 will be plenty to launch my cat photo sharing app. Once I need to scale, I can use tools like node balancers and backups, and Linode has built-in dashboarding and metrics so that I can see the traffic to my Linode servers, and I can understand how many of my users are posting cat pictures and looking at each other's cat pictures. Go to linode.com/SEDaily and get $20 in free credit today. The plans start at $10 a month, so it's a great deal. Thanks to Linode for sponsoring Software Engineering Daily. Now let's get on to this episode. Dor Laor is the CEO of ScyllaDB, a database that is compatible with Apache Cassandra. Dor, welcome to Software Engineering Daily.
Hello, and good afternoon or good morning, wherever you are. Thank you for inviting me.
Absolutely. So let's start by talking about Cassandra, and then we will get into ScyllaDB. So, we've done a couple shows on Cassandra, but I think it can be confusing for some people. So why don't you give us an overview for what Cassandra is and why people use it?
So Cassandra is a NoSQL database. NoSQL stands for not just SQL. You can ask Larry Ellison because he said recently that Oracle is a NoSQL database as well because it's included SQL. Yeah, the guy has sense of humor and money, so I bet he's right. Cassandra specifically is one type of family of databases within the NoSQL that they can get segmented into subfamilies as well. You can find the document store databases like MongoDB and Couchbase, which are kind of schemaless, and you store there not real document but JSON objects, which is really good to get started. But later on, they can bite back because you haven't given a lot of thought for your schema, and that's why you'll get probably less valuable data out of it, or then later on discover that the schema actually resides within your data, and you'll have difficulties that related to that. Cassandra is part of the family which is more of a table, but more like a regular SQL database, but without transactions and without joins. Cassandra, so you can think about it just as a table with columns and rows. Specifically, Cassandra and also Scylla, because it's just compatible, has a wide row structure. I'll cover that soon, but basically it means that within your cells in the table, you can store them not just standard fields like int, string, or binary blob. You can store their tiny tables and subcolumns inside of them. So it's schema full, and you can manage schema. And the advantage, the big advantage of canceling transactions and joins is that you can scale out very, very, very well. Cassandra can scale up to dozens, hundreds, and even thousands of nodes in a single cluster. To the best of my knowledge, it's the best distributed database or distributed infrastructure out there, because all of the rest of the gang don't scale that much. And just to be sure, it keeps all of the results consistent in disk. So it's not an in-memory solution, because data gets written to the disk. And that leads me to another subset of the NoSQL family, which is the in-memory type of key value stores like Memcache or Redis, which allows you to keep data in the cache and respond pretty fast. But normally there's either schemaless, just provide key values. Sometimes they provide more sophisticated verbs. And normally they don't. They are semi-persistent. So data isn't synchronized immediately to the disk. There's quite a big of a lag, and also there's a limitation that you can't store more data in the disk than your RAM size. So everything has its advantages and disadvantages.
So you mentioned that Cassandra does not have transactions, and when people hear that, they might be like, "What? That doesn't make any sense to me." So you can't write to it, or you can't delete from it. Describe what that means. Like, when you say Cassandra doesn't have transactions, what do you mean by that?
Mm-hmm. So actually, Cassandra do have some type of transactions that are recently new, not that new. I think it's around 2 years old, but they are called lightweight transactions. But if most of the users don't tend to use them, so let's focus about the non-transaction type of Cassandra accesses, which is the most common ones. It means that you access the database and you store the information there, but in a non-transaction way. So it's sometimes it's quite tricky, and I actually explained that today for a customer. So when data reaches the database, Cassandra has a configurable replication factor. So normally you wouldn't just store the data in a single node, but you're going to replicate it into other nodes. And normally people just choose quorum. So once the data reaches a quorum of subset of your cluster, then the client gets an acknowledge back, and disk writes happens. However, this isn't quite a transaction, because let's say you started the write process, and the coordinator for this operation, which is the node that the client access first, client can access. There are kind of different criteria to picking a node, but any node can be a coordinator. So when the coordinator starts sending the writes to all of the replicas and waits for a majority, let's say if it's a quorum, let's say there is a failure and the entire network failed for some reason, and just a single server accepted and actually managed to write the data, and all of the other servers failed. So of course the client, either the coordinator managed to send a negative response to the client, or the client didn't hear and timed out. So the client assumes that the data didn't reach the cluster, and it's okay. But actually the data did reach one node, And when the cluster will get reconnected, the data will get propagated to the other nodes in the cluster because it wasn't a transaction. You can think about transaction, a simplified way of transaction is two-phase commit. So there wasn't any two-phase commit here. And that's why data that reaches a single node can still be there in the database. So that's something that users should think about.
So I think the distinction that you're drawing is when we talk about transactions in traditional databases, you could tell me if this is correct or incorrect. When we think about transactions in traditional databases, we think about these atomic, like you said, two-phase commit or three-phase commit or whatever, where you have strong consistency guarantees. And with Cassandra, it's more of this append-only log of things that are happening across the data, and nodes just catch up as they get the chance to, and the delete process, the delete process uses tombstones, and that's the eventual consistency version of a delete. But the main point is that you have this eventual consistent transaction log of things that eventually propagate to all the nodes, and that is in contrast to the strongly consistent two or three phase commit type of distributed database. Would you say that's accurate?
Yep, it's quite accurate.
Okay. So as we ease into the conversation of ScyllaDB, we should talk a little bit about the query language that Cassandra uses. So Cassandra uses a query language called CQL. Why does Cassandra need a unique query language? Why can't it use an SQL variant or a query language like Mongo?
So CQL tries to mimic the more sophisticated, feature-rich SQL verb. So it's kind of similar, and if you're familiar with SQL, you feel at home relatively fast. However, it lacks features like joins, and some of the aggregations aren't there, and that's kind of a limitation. Again, those features were dropped from the database deliberately in order to allow better high availability and better scaling out. So there was an intention and was thought were given to these things. I think that as we go along, then there is a convergence in the database world. So the CQL language evolved, and you can see things like secondary indexes and materialized views. You can store JSON or pass and extract JSON objects. The where clause evolved in CQL. So I think that there's a fairly good chance that CQL and SQL won't be that different if we'll look at the medium-term future. And if we compare what Cassandra had in the past, it was almost schemaless when the Thrift protocol was used, and there was no good language like CQL. So eventually it's a good midway a compromise, and going forward, I think that eventually we'll see SQL, almost a full SQL form. I mentioned before that the lightweight transactions exist in Cassandra, so many times you may not need transactions for data that is about recommendation engines, social information data, IoT data, but you would want transactions for data like user IDs, passwords, etc. So that's why lightweight transactions were added. Nice thing is to observe databases like Postgres, where they try to add more of a JSON verb. So that's why I claim that convergence is starting, and all of the database will move in the winning languages, and the winning verbs will eventually be more common in more databases.
What are the shortcomings of Cassandra?
So there's a couple. So first, no joins and no acids. So, but I think that users are used to it, and that's why there is no SQL databases beyond and just normal SQLs. But beyond that, there's a couple of things. First, Cassandra uses log-structured merge tree. It means that append only, and you mentioned that deletes translate to actually writing data, which is the tombstone. But in the background, there is no magic, and it makes writes very, very fast. However, it comes on the expense where should be a background process called compaction that needs to, in the background, the database needs to merge all of the copies that were written to a single key just to keep the latest and greatest form, and collapse all of those tombstones so the disk won't get filled. So writes are relatively fast on the expense of reads, and also on some expense of administration burden, because a database a person or DevOps person needs to manage and tune the database. So that's one thing. Fast writes on the expense of reads and some admin burden. Second of all, it uses Java. Java is a terrific language for management, but not for high-speed I/O. It has given to the developers a relatively fast start, but as it's evolved, then it's just a pain, and Cassandra developers try to constantly move objects from the heap to off heap, and that's of course defeats the purpose, because why do you use Java on the first hand? You'd like to let the framework handle the memory management, so they don't get to enjoy from the features that Java provides, and they do suffer, and Java users suffer from very complex tunables. They suffer due to garbage collection, which eventually reach a phase it's called stop the world, and all of the threads need to stop and make sure that the garbage collection will run and clean the memory. As the amount of RAM constantly increase, and not to mention new memory model like non-volatile RAM approaching, then the problem will continue to grow and grow. So that's quite painful for the user. So I would say, and eventually it translates to large latencies, unpredictable latencies, and also the performance level that a single node can provide aren't that good. Cassandra uses off-the-shelf Java and uses good generic mechanisms that comes from Linux, like the page cache, which is terrific for caching disk accesses. But since it's generic and not tailored, then it's not ideal for performance.
Right. So you've touched on all these shortcomings, and many of them are essentially leading to some severe latency that you have improved upon in ScyllaDB. And ScyllaDB is a NoSQL column store database that is compatible with the CQL query language. So this is essentially a database that is Cassandra compatible. You can drop out your Cassandra database and replace it with ScyllaDB. That's at least the claim. So explain why you started building ScyllaDB.
So I'll try to shorten the long story. In the past, we built a unikernel called OSV, which is still a project that we support or try to support in best effort, but it's not relevant to Scylla today. And we wanted to run variety of workloads. It was optimized for Java mainly, not just, but for Java. Cassandra was one of the sexiest workloads we wanted to support. And while our OSV operating system, and we had our own kernel, had a really fast and slim kernel with our own TCP/IP stack, we saw that we managed to boost the Redis performance by 80%. And when we executed Cassandra, then the performance gains were almost lost. There were sometimes gains of 20% more, but sometimes it went away. And we observed that although enough resources are given to Cassandra, Cassandra can't utilize all of them. So we understood that there's a large opportunity for improvement. We know that some companies that run 1,000 clusters of 1,000 machines, at the time, Google engineers published a benchmark of using 300 Cassandra virtual machines in order to reach 1 million operations per second. And coming from a system programming background, most of us came from the KVM project, the hypervisor. Then we knew what modern machines are capable of, and we knew that it's totally ridiculous. Like a single machine can do this type of performance, and we proved that that's what we thought before, and that's what we proved today with Scylla, because we have benchmarks that show that a single machine can get to 1.8 million CQL requests per second, and that's quite dramatic improvement.
So Scylla's approach to NoSQL design, obviously you mentioned the fact that it takes more advantage of the fact that Cassandra or a Cassandra-like database takes 100% of the CPU, 100% of the memory. But the Scylla's approach is also optimized for modern hardware. What are the trends in hardware that has shaped your strategy with Scylla?
So it goes the following. There are multiple things. So the first one is multi-core. CPU speed stop increasing in terms of frequency, and transistors get added. Let's not argue about whether Moore's law alive or not, but frequency stopped rising, and instead we have more cores, and it's very challenging to utilize all of those cores. When I was managing the KVM project, the performance team couldn't find a benchmark that utilized more than 40 to 80 cores because the benchmark itself wasn't scalable. So it's quite a challenge for software. The design that we took with Scylla is the design that uses shard per core notion. It means that apart from the fact that we do sharding like many other distributed systems that all do sharding in the cluster level, and we do the exact sharding that Cassandra uses, within each node we use additional level of sharding, which is transparent from the user. Each shard has a core of itself. Storage people call it thread per core. And it's the exact thing, but extended. So our shards has a single core, or more accurately, hyperthread. They have their own memory, so we divide the memory per shard logically, and the memory is always NUMA local, because accessing the local memory that resides on your socket is way more, twice as fast than accessing remote memory on some other socket. And if there are local I/O devices like multi-QNIC, or sometimes in the future coming up multi-Q storage devices, then we'd access these devices directly by the core. And the idea is to be lockless, because each such an internal shard owns its data. So there's no need to lock the data. There's no locking whatsoever. Locks in x86 are pretty expensive. First, when they're contended, and the more cores you have, then the more contention that you have. So there's a likelihood that some other core will own that lock, and the other cores will just go idle. And even if there's no contention, and their locks have fine granularity, just obtaining the lock, you need to lock the bus, and it's very expensive. So one mechanism is the multi-core, and the answer for it is shard per core. That's one.
So you have mentioned these hardware characteristics that you're able to take advantage of by re-architecting some of the things that Cassandra does in Scylla. Could Cassandra just be re-architected to take advantage of these characteristics, or is there something that is holding Cassandra back from taking advantage of these same hardware trends that you mentioned?
So the answer is yes and yes. So the Cassandra developer observed, naturally they observed Scylla and observed the design. We're open source, and most of, not just the code is open, but also many of our internal discussions are open in our presentations, and probably this talk as well. So they try to re-architect Cassandra and have this move away from SEDA and have a similar thread per core approach without just regular polling. We know that there's some active work about that. However, they don't have a chance to reach the performance level that we have, because when you're using C++ like we do instead of Java, then we have direct access to all of the machinery and direct system call access and full control of the machine. When we compile the code, we check and verify that the object code is efficient, and we don't do just there are no wasted virtual function calls, etc., etc. So I believe that they'll improve in time, but not to the level of performance that we got.
So I think also one kind of edge you have is that Scylla is started from scratch in C++. So obviously there are things that you can do in C++ that you cannot do in Java. Maybe you could touch on the difference between these two. So I guess first, like, why was Cassandra written in Java? Was it just that, well, you could just talk about why Cassandra was written in Java, and then what does C++ provide for these purposes that Java cannot?
So without opening a religion war, then always C++ is a low-level language, while Java is high-level one. So lower-level programmers will always have a benefit. They may need to. It may take longer time to develop, but the outcome's supposed to be better. Why they chose the Java? Many big data projects start with Java. There's good things that happen in Java where it's relatively easy to share code and share packages, like thrift implementation, and you can just potentially load a Cassandra jar to some other project, and right now you merge the two. So there are benefits coming from the Java world. In C++, there are libraries like Boost, which provides you great basic building blocks, but not to the level of protocols like thrifts, etc. But I would choose C++ over and over again and again. It's not just a personal choice, but it's the more rational choice when your goal is to maximize the machine resources. Like we just started to speak about recent trends in computers, so multi-core is just one of them. And again, Java has a problem because there's always the state of garbage collection in software world. Beyond that, then it's the increasing amount of memory, where the Java heap is relatively small. In the past, the standard collector had like a recommended heap of something between 8 to 16 gigabytes, and that's it. Later on with G1, then I think G1 can do 64 or 128 gigabytes of data, but that's still isn't that much. recently Amazon released a 2 terabyte machine, and I guess it will just grow with the non-volatile technologies. So it's not just the multi-core, it's the memory as well. And accessing devices directly, we just started with the performance world. So we didn't cover that, but we support two types of I/O stacks. We support the Linux TCP/IP stack, the standard one, and we have an implementation of user space TCP/IP with the same reactive model implemented in C++ that we have, which provides twice the performance when we implemented a protocol like Memcached. So in the future, we're going to, it's already works with Scylla, but it's not hardened yet. And but in the future, we'll see another level of performance gain. Similar things are with the file system. We use handful of technologies, our own caches. We bypass the Linux page cache, and we plan of having our own file system. So we won't use standard off-the-shelf file system and go directly to the block devices.
Free Code Camp is a free community for learning to program. Whenever I hear somebody say, I want to learn to code, but I have no idea where to start, I suggest that they check out Free Code Camp because it's a free community of over 300,000 developers learning to code together. Learning to program alone can be isolating, but the community at Free Code Camp is friendly and always willing to help. That's why it's such a great community to join as a new programmer. Other ways of learning programming can be expensive, they can be intimidating. Free Code Camp costs no money. There's no risk. Free Code Camp will teach you how to write code and work on projects for nonprofits. This lets you build a portfolio of work that you can show to potential employers and then get a programming job of your own. Free Code Camp did not pay me for these ads. I am a huge fan of Free Code Camp, and I want to show my support to Quincy Larson and the rest of the team at Free Code Camp with some unpaid advertising spots on this show. If you have a friend who wants to learn to code, send them a link to Free Code Camp. Tell your mom, tell your sister, tell your grandfather, tell your brother. Programming is the ultimate creative tool, and everyone should know how to do it. Free Code Camp teaches you to do it for free. Thanks to Free Code Camp for doing your great work, and let's get on with Software Engineering Daily. So when we're talking about ScyllaDB, we're talking in these abstract terms. Let's make this a little more tangible. Could you walk through a read and a write with ScyllaDB and explain how each of these respectively compares to a read and a write in Cassandra?
All right, I'll do that. I think that my developers are way better than me, so it's certainly about the Cassandra read and write path. But I'll try to explain.
It doesn't have to be too low level, just maybe enough to highlight the differences.
So basically, the similar thing is that the client has a read request, and it picks a coordinator, which is just one of the cluster nodes. Sometimes coordinator get picked by their proximity, so the nearest node will get picked. It's again similar in the between the two databases are identical in that respect, and the same client is used by both databases. So the coordinator parses the CQL request, decides that it's a read request, and what we do is we issue a read that goes to the local disk, and in parallel, asynchronously, we issue a read to a number to the number of which is the table is configured to, or this specific operation, because you can have even special. each operation may have its own configurable semantics, configurable consistency. Let's say it's a quorum, so for simplicity. So the cluster needs to collect a quorum of requests, of read requests from the majority of the servers in the cluster. The idea behind it is that since it's a eventual consistency database, then you'd like to consolidate data that it may be more recent. So the coordinator starts collecting all of those reads asynchronously, and when you get large enough majority or large enough number, then the answer propagates back to the client. So that's identical with the two databases. Sometimes it goes even for more interesting cases. If the data isn't the same when returned from all of those quorum of nodes, and there is a difference between the version of the data, then the entire data set will get the entire set of replicas that own this token range will get queried, and consolidation will happen in the background. And just when the quorum will reach consolidated a quorum of the servers, then the data will propagate back to the client. Pretty complex, but identical in the two databases. Now, what we do is for the reads, we issue reads with ODirect. It means that we bypass the page cache, and we manage our own cache. It's a really important advantage, because if data is in the cache, then we'll immediately respond back. If data is not in the cache, then we're going to issue a synchronous DMA operation for that disk access, and we'll just read the exact object that we were asked for. So if this object is, let's say, 512 bytes, and that's, I picked this number because it's a sector of the disk, of smaller disks, then we'll just read this exact sector, and that would be it. Now, since we have the notion of thread per core, within each of those threads, we have our own scheduler. So once we issue this asynchronous DMA, immediately the disk is slow relatively to the CPU. So we'll immediately deschedule this context, and we'll go to run some other context. With us, we don't have threads, so these contexts are basically lambda functions. And our cores are capable of running millions of lambda functions. We can do 1 million operations per core of these lambda functions. So it's very, very fast. And when the disk returns, then we release the answer back to the client. In the Cassandra case, and it's kind of similar, not just to Cassandra, but for standard multi-threaded applications that uses the Linux page cache. What happens is that a thread from the listening pool gets scheduled, processes the request, and start issuing all of the requests, hopefully asynchronously. Sometimes not all of the network requests for the replicas to retrieve the read may not be fully asynchronous, or they may still consume threads. So sometimes if you have a lot of requests going on, then you may exhaust your thread pool. In addition, let's say the data is not in the cache. The application, Cassandra, the database application in our case, doesn't have the knowledge that the data is not in the cache, because the one who manages the cache is the kernel. So it just accesses the data, but the kernel issues a page fault. And page fault is pretty expensive operation. The thread gets descheduled. It's heavyweight in terms of CPU and also in terms of latency. And if you have limited number of thread pool, then the context of the threads will get blocked until data will get back. So you couldn't do 1 million operation per core of these accesses. You can do thousands of them. And that's pretty significant difference between the two.
So that's a great comparison. I think that covers a lot of the ground of how the two databases differ. What about the scalability model? How does ScyllaDB's scalability model differ from Cassandra's?
It's an easy question. It's not. In terms of scaling out, it's the same thing. So we have the gossip protocol. We have the multi-data center protocol. We have snitches. It's exactly the same. And you can scale to hundreds and thousands of nodes. Usually with our performance, then there's no need to reach 1,000 nodes, but you're certainly capable of doing it.
Okay, so then a question that has less similarity with the two databases. What about memory management? ScyllaDB has no pauses under compaction or garbage collection. In Cassandra, how often does the cluster undergo compaction or garbage collection, and how does this inhibit performance?
So the two databases, and it's not just it, many databases that have a low structured merge tree or just need to update new nodes that joins the cluster, have background operation, as opposed to the foreground operation, which are the regular I/O processing and semi-transactions. So what would a standard user would desire is that the foreground operations will have SLA, which won't get hurt by the background operation. Because if you're in the process of streaming data to a new node or doing compaction, then most times then you can wait a little bit longer, and you'll prefer that the foreground operation won't notice and not encase in throughput, and you won't hurt latency neither. And that's quite a painful area in Cassandra. For instance, in all of those operations like compactions, repair, and streaming, Cassandra has static configuration for them, and you can limit those operations like in streaming, you can limit it for 25 megabytes a second. And this way, let's say that you have enough bandwidth more than that, so you're guaranteed that it's a weak guarantee that foreground processing won't get hurt. But it comes in the expense that streaming will take a very long time, and if you have, let's say, terabyte of data in your nodes, then it hours and days will go by until you'll manage to stream it up it all to a new node. And that's really a real problem, especially if you'd like to decommission an old node in favor of a new node. And that the same happens with compaction. You may not compact fast enough. So if you put the thresholds too low, then you'll fall behind with the background operations, and you'll suffer. If you fall behind compactions, then you'll have multiple stable files, and in order to read, you won't just read a single file. You'll read a lot of files, sometimes dozens of them, for a single read operation, and that's horrible for performance. Instead, we dynamically set this balance and control this balance before we even boot our Scylla daemon. We run a simple automatic script that basically it's a benchmark. And the purpose of this benchmark is to calculate the sweet spot of maximum disk concurrency. If you increase the disk today, that's also related to your questions about modern hardware. If you take SSDs, it's not just one rigid format. It's composed out of dozens and maybe a lot more of smaller disks or units combined together. And that's why you can access the disk concurrently. But there's a limit to the number of concurrent requests, of course. There's a point where you add concurrency and you get better throughput and still keep your low latency. And beyond a certain point, let's say beyond 100 concurrent operations for modern fast disks, then requests will just queued up by the disk controller. They may also be queued by the file system code as well. Our benchmark script automatically finds this sweet spot, and we have an I/O scheduler with inside in user space inside Scylla. It's something which is totally transparent from the user. Now, this I/O scheduler role is to make sure that if we do not reach the point of maximum disk concurrency, then it goes in full speed ahead and just forward all of the requests directly to the file system and later on to the disks. So it means that if you're compacting, then you can compact in 1 gigabyte per second if you do not have foreground workloads, high workloads. However, if you have parallel workloads coming from the background and from the foreground, then our I/O scheduler do not fill the disk beyond the point of maximum concurrency, and it has its own prioritization mechanism. And we have different classes for reads, for writes, for compaction, for repair, and for streaming. And dynamically, we set a priority between them. So as long as it's not a must to compact, then we'll prioritize writes and reads, and latency won't get hurt a bit. And that's how the system works. And the benefit is not only to have very good performance all of the time for your background and for your foreground operations, then there's no hassle, because tuning a Cassandra system for that is pretty a nightmare. And even if you manage to do that, then it will be accurate just for the particular workloads that you tuned it, or the particular machine that you run it on. If the characteristics of your workload or machine change, then you'll need to tune it all over again. And in our case, no tuning whatsoever. We do that automatically.
Okay, so we've talked a lot about the technical internals of ScyllaDB and how it compares to Cassandra. I want to talk a little bit about the business model and the ethos of the product and the company. So ScyllaDB is not open source in contrast to Cassandra.
It is.
And
it's actually,
it is open source.
Yep, it's full open source. So today,
I'm so sorry. I was totally confused about that.
It's off by one. That's fine.
When was it? Has it always been open source?
Ever since we went out of stealth mode last September at the Cassandra Summit. So
wow. Mm-hmm. Okay, I'm so sorry about that. I don't mean to spread the misinformation that I must have read at some point, or I'm not sure what happened.
It always has been open source, and in return you can go and just mark a Stark or git clone the code.
Okay, that's totally fine. Then what's the business model like for ScyllaDB, the company?
Here we didn't innovate much. Our strength is in technology, and in business, we'd like to do fair business as many as other open source vendors. We worked at Red Hat before, and we're familiar with the industry. And our business model is subscriptions. So those who would like to consume our open source bits, we welcome them, and we actually encourage them. Today, there are sometimes we participated at Percona Live, and back then, we presented, and we discovered that there are folks running Scylla in productions where we didn't know even that they were using it. So that's the open source. We actually have more than a single open source project. There is the Scylla, which is an end user database, which you consume, and there's also the engine behind Scylla, which is called C-Star, and has most of the sophistication that I described. And that's another independent open source project that we created for Scylla. But one can take the C-Star project and implement another protocol and try to replace some other old-fashioned system with it. So that's the open source. In terms of business, then we're a company, a VC-backed company, and we definitely need to be profitable. So we do subscriptions, yearly subscriptions, and in those subscriptions we provide support. We provide a long lifetime guarantee and a enterprise version of our database.
So one area that I think is interesting about the business and just about the project itself is the fact that you can kind of take advantage of some things from the Cassandra community because you are CQL compatible. And it reminds me of a show that we did recently with Citus Data, which is a PostgreSQL extension that makes distributed Postgres easier. And one thing that the guest from Citus, Osgun, he said was that when you use the Postgres extension functionality, you can extend Postgres. And you don't want to, because you don't want to fork Postgres. You don't want to fork it because then you lose all the support of the open source community. And but what I heard when I was preparing for this show was that ScyllaDB, despite being a complete rewrite of much of the Cassandra functionality, because it's all in C++ and you do all these things differently, you can take advantage of things like the Cassandra Spark connector. Which is pretty interesting because in this case, you actually are getting to leverage some of the developing things that are going on in the Cassandra community. So I'm just curious to what extent that is the case, where you can leverage the ongoing development of the Cassandra community, despite being a completely different database.
Mm-hmm. So the difference between the two examples that you've given is the location of where those tools hook. So in the Postgres case, then the plugin runs in the context of the database. So you can utilize the underlying layer there, and it's a plugin that gives you additional functionality, if I understand that correctly. We're on the it's mostly the Progress model. We uses everything beneath and provides additional functionality on top of it. In our case, it's kind of the opposite, where we re-implemented everything underneath, but everything on top of the database of each of the databases, meaning either Cassandra or Scylla, remains the same because we're compatible in CQL wire protocol. So all of the client sides remain the same, and the only way to access the database is using a client. So that's the way Postgres that's the way Spark accesses Cassandra or Scylla using CQL. That's the only connector possible. The same with ODBC driver or a Presto project that has Cassandra bindings and works nicely over Scylla, or some other time series databases like CairoDB and so forth. So all of the tools, all of the client sides remain the same, just the database is replaced.
Okay, so as we begin to wrap up, I'd love to know what the ScyllaDB team is working on today and what is in the future for the project.
All right. Today, we actually, this very day, we released 1.2 release of ours. This 1.2 release included items that were left in the from before, like alter key space functionality. We added CQL compression, so you can compress the client to server protocol, and a bunch of other goodies. Mainly, I can say that we were really busy, and we also reduced latency. We have a very interesting technology blog where we blog about our latency journey. And I really recommend readers to go to that blog in general, in particularly about the latency gains that we just released. They were not related to Scylla, because Scylla is a regular Linux process. So if you go to that blog, you can read about our journey, about tuning the Linux scheduler properties, tuning C groups within Linux, tuning. We have a Java JMX proxy daemon, which in order to keep compatibility, so users will able to work with Scylla the way they work with Cassandra using the Node tool, we added a Java process just for admin compatibility. And guess what? This tiny Java function process increased our latency. So we had to handle it as well. So eventually the maximum latency we measured was 1.8 millisecond. That's the maximum, not the 99 percentile, but the maximum latency. Anyway, that's what we released today. And I think in around the next 2-3 months ahead, we'll close some gap that we have with Cassandra. It's totally compatible, but there were several small features that we were left behind, like sometimes small but important, like secondary indexes and materialized views. One compaction strategy got left behind, so date-tiered compaction will come next month, and things of this sort.
Cool. Well, Dor, thanks for coming on the show. This has been a fascinating conversation. I feel like we went deep into Cassandra to the level where we were able to compare it to Scylla, which is, I feel like it's a great accomplishment for the listeners. So thanks for coming on the show, and great continued success with ScyllaDB.
Thank you very much. It was a pleasure.
Okay, likewise.